Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 69. My name is Joseph Darnell, and I'm joined by my good friend in the studio again, Dr. Robert Carter. Hello, Rob.
Hey, Joe.
How's it going?
I'm doing great. How are you doing?
I'm doing really good. This is the end of the week, and I'm going to enjoy the weekend.
Me too. Last weekend was no fun. 3-day weekend, and I was home all weekend, quarantined.
Oh, man.
Blah. So this weekend, I'm free as a bird. And it's nice weather, too.
Yeah, just yesterday here in Georgia land, it dropped. It dropped to
and
a nice,
humidity
crisp
dropped.
66 degrees. So good.
So we'll have a couple nasty days before it really sets in nicely, but it gives me hope that between now and March, it's outside weather.
You know, I don't know enough about the insect life in Georgia, but I noticed something over the past season, early in the season, in the spring and the summer. There was more ants, fireflies, of course.
Okay.
I didn't see a whole lot of flies, but then the flies came along. It kind of came in waves of very mild plagues. The ants went away, the flies came, and then the flies went away and the beetles came.
Interesting.
The beetles went away and then spiders came.
Yes, the big long-legged spiders.
Well, not
the wispy things in every corner of your house.
Yes, those,
yeah.
yes. But not the wolf spiders. We're going to get to that. We haven't seen the wolf spiders yet.
Yeah, I put my face in one of them yesterday. Big
Chills. Yeah, for real. Oh, okay. So anybody who doesn't know what wolf spiders do, they typically like to stay on the ground and they gallop like cheetahs.
Oh, yes. No, actually, yeah, I was referring to the garden spiders.
The garden spiders, the ones
that's as big as your thumbnail, and they make.
Are they got a little bit of yellow and gray on them?
Often, or red, or lots. And they make
super creepy.
They make webs right at face level.
They look like spiders that are trying to look like warning signs for construction zones.
Yes, interesting.
Yeah, with like a cockpit, the ones that have like a silvery finish to the top of their head.
Yeah,
they're really weird. It looks like an opaque cockpit you can't see into.
Yeah,
cyborg spiders.
Cyborg spiders.
Wow. Moving on to things.
Insects.
Oh yeah. Okay.
How are your bees doing?
Oh, they're doing very good. We actually got into the hive just the other day.
Oh, good.
And we saw honeycomb.
Yes.
But no honey in the comb on this side of the frames 11 through 20.
Same with mine.
Good news was, though, that looking at all of the hives on the brood side of the box,
yes,
the comb top to bottom. Comb top to bottom all the way to...
Honeycomb or brood comb?
Well, okay, mixed. So mixed, yes. So like frames 1 through 10, they've got comb down to the bottom of the frame.
Okay.
Which they didn't have last time we saw them.
Okay. Filled or just empty comb?
I want to say mostly filled, even over 10. I wasn't looking closely, but I want to say that there was stuff on most of it. And on the side where they didn't have comb, frames 11 through 20, there were a lot more of the girls over there checking it out. And I'm really wondering if they're just disinterested in the black frame comb templates that we put in. Like they just don't like that stuff.
Yeah. I don't know. I'm worried about that too.
Weird.
But mine are, most of the frames that had honey on the peripheries do not now. They're empty. The last time I checked a couple of weeks ago, but they had a lot of brood comb. And then just the last couple of days, all of a sudden there's an explosion of bee population. I have a lot more bees, and they're the young bees because they're outside with their faces on their, poking at the outside of the hive like they've been doing all summer for some strange reason. No one knows why, but those are the new ones.
Oh,
and so I know I have a new crop of.
Maybe it's like they're cutting in their teeth. They're stretching and
don't know,
solidifying their stinger.
Well, stingers at the other end.
Oh, yeah. Okay. Pinchers.
Okay, maybe, who knows? But they are there, and I have a lot more, and they're buzzing. I notice a noticeable difference in the sound of the hive, and it smells.
Smells like isn't just a stronger,
the honey propolisy sort of smell, musty, sort of like, oh yeah, they're doing something in there.
Yeah,
because they weren't harvesting for the last 2 months, and I've been worried. And all of a sudden, there's at least 3 different colors of pollen.
Interesting.
Just over the last couple of days.
So
maybe I mentioned it last week, maybe, but
that reminds me, the one thing that I did notice on frame 10, you got the comb from top to bottom, and the comb in the middle has a darker tinter to it, like they got some dirt or something mixed in with the wax. And it almost makes like the impression that the bees were trying to make a bullseye in the honeycomb.
Interesting.
Because all of it outside of this dark region is the pale yellow. And then right there, about the size of my fist, in the middle of all the honeycomb, is this brownish murkiness to the comb. And I don't know why.
Very curious. Well, if you do harvest that particular frame, you can cut out that section and see if that section tastes different than another section, just for fun. Because
Yeah.
you can.
Yeah, because you can. But then again, I don't know what dark brown. Maybe the bees were throwing up and had a case of the bee flu when they were constructing that zone.
No, I doubt that. No.
Okay.
I don't know though, but I have been feeding my girls.
Yeah.
Sugar water every day, every couple of days, just because it's been a long dearth. I don't think it was a good harvesting summer for them.
Yeah.
So let's go fall. They need to pack away enough food so they can survive the winter.
Oh, I remember now what I was going to tell you about the insects.
Yeah?
So yesterday I was enjoying a cigar and doing some reading, playing a little gaming on my Switch out on the porch. I smoke cigars occasionally.
Yes.
And it got dark outside and I had the light on the porch. And I noticed that the current plague is moths. And there was moths all over the porch, but hardly any of them that were active. They were just chilling. It's like 10 o'clock at night and they're just hanging onto the walls and onto the ceiling of the porch. And I wondered, why moths now? Like, why did I hardly see any moths all summer long? I don't know. And these are like the size of the bone in the tip of my index finger.
Okay.
They're not terribly large, an inch to an inch at the most.
All right. All I can say is that particular species of moth is about that size, about this time of year.
Okay.
Don't know anything more than that.
I did see a beautiful hummingbird out in my tree the last, I don't know, maybe Tuesday.
Cool.
Beautiful thing. And I don't normally notice the hummingbirds around my area. So that was just a wonderful thing.
If you had a feeder, you would definitely notice them. Or if you had planted plants that they liked, they would be hanging around a lot more.
Have you seen any of the hummingbird moths around here? I think I spotted one of those.
Not this year. About 5 years ago, I definitely saw one.
Okay, because I think I've seen two this past summer.
Cool.
Just like flying through the property,
Cool.
going from one tree to the other, but too fast to really distinguish them.
Yeah, but you're like, that's not a bird. Wait a second.
Yeah. You always do a double take. Like, is that a glitch in the Matrix? What is that?
Speaking of glitches and matrices, we wouldn't have a matrix without a computer.
Yes.
We wouldn't have
what you did there.
glitches without computers. In fact, were it not for cosmic rays, we would have accurate computers that never randomly change their memory. But cosmic rays interfere with our computers in bad ways. Either way.
What are cosmic rays exactly?
They are, great question. I did not know this
Because that
recently.
sounds like it's a glitch in the universe. Cosmic rays in the ether.
They are high energy particles streaming at us from outer space. So hydrogen ions, that's a nucleus without any electrons. Helium ions, that's a nucleus without any electrons. But even some heavier things like iron, charged particles, and they're coming really fast. And because they have a lot of energy and a charge, when they hit a molecule, they can break it and cause cancer and things like that.
Wow.
Yeah.
There's a lot more to cosmic rays than I realized. I just thought it sounded like a reddish haze that was flaring off of a sun.
Well, I always thought it was like radiation, like light,
Something like that.
X-rays and things like that. But no, it's not. It's not X-rays. We would call it X-rays.
True.
Actually, particles.
Crazy.
Yeah.
All right, but anyway,
Right.
so the subject is computers. Computer science.
Well, at the most basic level that we can describe it. So, like the history of computer, why they invented a computer, what it is, what happens on the inside.
Yeah, can I?
Yeah.
I find this so weird that as the years have gone by, I understand CPU, GPU, RAM, motherboard, logic board, bits and bytes, teraflops and terabytes. I understand the components But then if I stop to think about how I get my job done on this computer and all the data it keeps straight and the programming of it, I don't understand. I don't understand how my computer is responsible for emitting sound from my speaker system, video imagery. What the heck are pixels? Understanding how this thing has it doesn't just do math, but it has a math app. Like it has a calculator for that. But then there's also the internet side of it.
This is great.
What is the brain of my computer?
This is awesome. All of those questions are high-level questions that can be answered with very simple things. And so that's what we want to do for you and me and the audience, because I learned a lot putting this lecture, is that the right word? Putting these notes together.
Material.
Yes, I learned a lot. And it's like, oh, I kept saying that as I'm studying this. But to start, let's go back to the beginning of the computer.
Adam and Eve in the Garden of Eden.
Well, a little bit beyond that. Charles Babbage.
Okay.
Early 1800s. The person who is credited with inventing the idea of a computer. He never built a computer, but he theoretically built a computer, drew out the plans for it. It never got made.
Is this sort of how Leonardo da Vinci designed flying machines?
Yeah. But no, this is Leonardo's ideas would never work, this flying machines. But Babbage's computer was built a couple years ago, and it works great.
But it wasn't built in Babbage's time.
It was not. Some things that he did build things that did work, but the computer was just a theoretical construct, and he drew it out. And he understood, here's what we need. Here's what is going to happen. We need this and this and this, and put that together. And we can do this and this and that and the other.
Wow.
And it was a computer. What happened was he was inspired by a man in France who invented a loom that could weave any pattern.
Really? I would not have expected it to start from there.
Me neither. But he used a punch card system where he would, code the pattern into a paper punch card, and the machine, as it's going zip, zip, zip back and forth. Oh, it's time to use a blue thread. Oh, nope, time to red. And it could do any pattern that you could punch out. Now, I'm sure there's some patterns you couldn't do, or some patterns you wouldn't want to do just because maybe you didn't have that many colors of string. But, given X number of colors you had and whatever else you might have available, you can say, okay, machine, do this.
So the original concept of the computer was created. It started from the desire to create, what is it called? Textiles? Wow. I did not see that coming. I would have thought it would have been motivated by doing rocket science and calculator mathematics.
Yes. No. But the next step is the rocket science of the day, nautical navigation. There are two ways that you can do navigation. Now, it takes a lot of math. If I'm sailing at 15 knots on a north-northeast trajectory with a 6-knot cross current, how long will it take me to get to Lisbon? Woo.
So the early stages are like the precursor to GPS navigation.
Yeah. So you could have a person hand tabulate all the numbers involved, and it's multiple steps. This and that and this and that and the other and the other. Okay, and here's my answer. And you might have gotten it right. You might have made a mistake and die on the rocks. Or you can have a bunch of people doing every single possible calculation and writing them all down in tables in the most boring books in the universe. Books of mathematical tables. And so you don't have to recalculate it every time. Someone's already calculated that number. Why would I want to do it again? Just go look it up in a book.
Yeah.
This row, this column, okay, there's my number. Write the number down. It'll take me 6.23 hours. Except those books have lots of errors.
Oh.
Because they're written down by humans and typeset by humans who aren't scientists. And so there are errors in the tables. And disasters happen because of some of those errors. And so Babbage said, you know what? I can make a machine that can automatically tabulate x squared plus 5 for any number. But what if I can make a machine that can also do 3x plus 2? And I'll put 1 in for x, 2 in for x, 3 in for x, 4 in for x, and it'll calculate y for me.
Right.
And just automatically just tabulate all the possible values of x for whatever function I put in. That was called
Earth shattering.
Earth shattering, yes. It's called the difference engine. And it worked beautifully.
The difference engine sounds like a movie starring Benedict Cumberbatch or something.
Yes, it does. But that's because he starred in the movie Enigma.
Yeah.
With Keira
The
Knightley.
Imitation Game?
The Imitation Game, yes.
Yeah.
Yes. But Alan Turing, famous computer scientist, he comes later. He's 100 years after Babbage. Turing gave us a complete computer, but Babbage he knew it. He understood what was going to happen. So he has this machine that can tabulate and print out all these tables. Beautiful. Took out the human being from the equation. But then he said, okay, so I can tabulate those things. I need another machine now. I need a machine that can literally do anything. Not just, y equals x plus 17. I need a machine that can do squares and cubes and, whatever I want to do. I need a machine to do anything. He called it the analytical engine. That was the first computer.
And that is a perfect way to describe computers in a general sense. Yeah.
Yeah. I want to be able to do anything.
The analytical engine.
The analytical engine. That's the thing he never built.
That also sounds like the name of a science podcast or
yes,
something.
It could be a good one.
The analytical engine.
Yes. He never built it, but he also ran into a young woman. She was 17 when he ran into her. They didn't have an affair or anything like that. This is, platonic, but she was one of the most brilliant people in the world ever. She was the world's first computer programmer.
What was her name?
Ada Byron, the daughter of Lord Byron, the poet.
Oh, see, that's perfect. Okay, little side note here.
Yeah.
I have to.
Okay.
So since I was maybe 18, I've always named my personal computers.
Okay.
And also, the ones I also use for work.
All right, that's very strange, but okay.
And you just said that her name is Ada Byron.
Yeah.
And that is perfect because all of the computers are named feminine and they all have names that end in A. I've had Felicia, Veronica, Amanda. I kid you not, like going down the whole list. And now I have
never
Ada.
thought of naming a computer.
Why not?
It never occurred to me.
Well, he named it the analytical engine. We could call it Anna.
I usually call mine stupid box. I mean,
my phone I named Ravenclaw. Anybody Harry Potter fans will get the reference.
Yes.
And my iPad is named Diana. And the work computer was the last time I was running out of the names that end in A, and I named it Gladys. So I'm glad I have another A name.
Now, this is just in your head, or you talk to your computer in first person?
No, of course I don't do that.
Well,
Yeah. But yeah, if you look up their hard drives, they're named these names.
Okay.
So Ada will be coming up next.
All right. Going back to Ada Byron, daughter of Lord Byron. She doesn't have a computer, but she's the world's first computer programmer. She, in her head, said, oh, here's how you would use this machine that doesn't exist yet. Here's how you would tell it to do things. Here's how you would get it to, draw a picture or run a mathematical formula. I guess she probably didn't say draw a picture, but, this machine that can do anything, it needs memory.
Oh, man.
It needs a place where you can manipulate information. We call that random access memory.
Oh,
it needs storage.
This is unbelievable. Like, why don't people talk? People talk about Steve Jobs and Wozniak and Bill Gates. Why don't people talk about Ada Byron?
Well, they should, and that's why we're doing it.
Yeah.
I mean, a young woman, and she gets married, has a couple of kids, but she keeps on working. And there's some controversy of who invented what and who thought of what, because she and Babbage are writing back and forth a lot and they're working together a lot. And I don't know, they're friends, but today we don't know exactly whose idea was what. That's how tightly they work together. So he was the inventor of machines, and she's the person who could look at that machine and know what it would do.
So he was responsible for hardware and she was responsible for software.
Yeah. Yeah. Someone was the Wozniak and someone was the Gates in that situation. I'm not sure who's who.
Wow.
Yeah. But could you imagine, spending time thinking about computer programming and you have no computer.
Yeah.
That is high level stuff.
We should have called them Babware and Byware. Babware and Byware.
Oh, I like that.
Yeah.
All right. Okay, so his machine is never built at the time because it's too expensive, too heavy, too big, too complicated.
Hmm.
It took the invention of the vacuum tube.
For vacuum cleaners?
No,
Oh, wait. Vacuum tubes are different.
the vacuum tube. It took the invention of the vacuum tube for modern computers to really start. I had an old vacuum tube amplifier for my turntable in the 80s, and you turn it on and go hum.
Yes.
That 60 hertz hum, and then it would get hot and start to glow because the vacuum tubes were hot. That's how they worked. They had to be hot to work. These things pulled an incredible amount of current. Very wasteful. Most of the energy going in came out as heat. But what the vacuum tube allowed was a memory gate. You could have a switch on the inside that could switch to the on or off position.
These are so simple, but what do you call profound concepts?
Yes. And the crazy thing is high level math can be broken down to ones and zeros. And that's the clue. This is what Babbage knew. This is what Ada Byron knew. This is what modern computer makers know. You have to be able to take the most complicated math and break it down into addition. When you think about it, multiplication is just addition. 5 times 5 is 25. No, it's 5 plus 5 plus 5 plus 5 plus 5. Okay. Well, subtraction is just addition, going backwards. Division is just addition, going backwards. It's all addition. And once you realize that, then you can start adding things together. If you can take all mathematical functions and break them down to something really simple, like 1 plus 1, then you can have a computer.
Oh, again, another profound concept. Oh, it's beautiful.
But all mathematical steps can be broken down into 1 plus 1 equals 2. If you want to add 5 plus 5, you know it's 10, right? No, it's 1 plus 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 1. You want to divide, you want to multiply, you're using ones and you don't even know it. 5 plus 5, you put it on your fingers.
Yeah.
Well, it's 5 ones and 5 ones, and you can see it on your fingers. But we skip over that in our heads because we get beyond counting on fingers because you just you got to memorize or conceptualize whatever it is. You take a step up. Computers they can't do that. We think computers are so intelligent. No, they are the stupidest boxes possible. No joke. They can't count beyond 1.
Oh, when you put it that way, they're just really good at counting to 1.
Really good at counting to 1.
Millions of times.
A million times and really fast. But it can only count to 1. But Babbage realized that, and he broke everything down into binary.
So why isn't it called unary if it's ones?
Ones, because there's a 0 or a 1. There's 2 possible states.
Okay. I always wondered why it wasn't not zeros and ones, but ones and twos. But then again, maybe
it could be ones and twos.
Mm-hmm.
No, because you need a 0.
Okay.
We could use computers that are base 10.
But we don't.
But the mathematics are so troubling. Just break it down into ones and zeros, man.
It makes sense, yeah.
Yeah, and in the future, we're going to have to talk about quantum computing. Quantum computing, they don't have ones and zeros. They have a 1, 0, and anything in between. That's why they're so fast, because they're not stuck with only calculating ones and zeros. So if you want to store a big number in a 1-0 system, you need lots of ones and lots of zeros to store your big number. And then we'll say, okay, what's that number again? You got to go read each bit at a time. It takes forever to pull that information. You have to store it somewhere else. Quantum computers anyway, you need to be able to break all mathematical processes down to binary, 1 and 0. And then you need to start doing logic. You need to start combining circuits. And this is what they did in the first vacuum tubes. Like, let's say you want to add 1 plus 1. What's the answer?
2.
2. Computers don't count to 2.
Can they understand 2 ones?
Yes. So imagine you have a wire with 2 switches, and you want to know if the switches are on or off. Well, you stick your finger on the end of the wire. If you're getting electrocuted, both switches are on. So switch 1 and switch 2 are on. That's called an AND gate.
Okay.
So if you have a place in memory that's set to 1, and that's connected to the switch. And another place of memory is set to 1, and that's connected to a switch. Your AND gate will have a 1 at the end of it because switch 1 and switch 2 are on, so the electricity flows through the wire to the end.
And if it wasn't on, it would have a 0?
There'd be a 0 there. If either one of them is off, it would be 0. It's not 1 and 2. You don't know which one is off necessarily, but there can also be an OR gate. Imagine you have 2 wires in parallel. Each one of them has a switch. They're connected at the end. You stick your finger on the end. One of these must be hot.
But it may be that one of them is not.
One of them, yeah, it's either both are on or one of them's on, but at least one of them are on. That's called an OR gate. You can start combining these types of gates together, and you can get an exclusive OR gate. That it's one on the other side only if only one of the switches is thrown. If both are thrown, it's a 0. If not are thrown, obviously it's a 0. This is digital. You're not worried about what's the voltage on the wire. It's just, is the wire hot or not? If it's hot, we call it a 1. If it's not, we call it a 0. And the voltage is irrelevant. Most of the time, we talk about 5 volts. Modern computers run at lower voltages, 3 volts, less than that. But 5 is a typical 1960s style logic would be a 5-volt circuit. And so you have AND gates, OR gates, NOR gates, exclusive OR gates, and all these different combinations of things. And it's just combinations of 1 + 1 = 2. But the way you arrange them, all of a sudden you can do complex comparisons, and now all of your mathematical functions open up.
So are you going to explain what circuits are?
Not necessarily.
Okay.
Because that would be a different area of electronics.
Okay.
But all we need is a power source and electricity running through a wire.
And the electricity running through the wire is a circuit?
Yes.
Okay.
If the switch in the middle is thrown, it's a circuit. The electricity goes all the way back to where it came from. Like one end of a battery to the other end of a battery.
Yeah. If
the switch is not thrown, then the circuit is broken and electricity cannot flow through that particular wire. But all a computer is a collection of gates that count to 1. We call them flip-flops. And not flip-flops that you wear, but a flip-flop is a circuit that will be in, let's back up a second. For computer memory, after you run some calculation, you say, okay, I got an answer. I want to save that answer somewhere. So you have to go to some place you call memory and set your answer. The answer is only in 1s and 0s. But when you set that answer there, you want it to stay. And so we have this thing called a flip-flop. And back in the day, it was a vacuum tube. And if you ran electricity through it in this way, it would flip over to one state, off. If you ran electricity through it another way, it would flip over to another state, on. There's your 1s and 0s again. That's your binary representation.
So is that the original, what do you call, like the origin behind the name floppy drives?
No, because they were literally floppy.
Yeah, I thought that's what it was.
Yeah.
But I wondered if it was
there might be some
misattribution.
There might be some way to go back to the flip-flop. Maybe, computer scientists are like, hey, it's floppy. Haha, I don't know.
Yeah. Okay.
But it was literally floppy. And then the hard drives came out. And it was literally a metal platter that you could not bend.
Right.
And of course, no one knew that until they started opening them up and say, hey, man, check this out.
Yeah.
I'm pulling out magnets. I love pulling out magnets out of old hard drives. There's strong magnets in there.
Oh, wow.
Anyway, so you need a way to compare 1s and 0s. And all mathematics can be broken down into comparisons of 1 and 0. You need a way to store that information. In vacuum tube flip-flop arrays, you can imagine you can't store a lot of information that way.
Yeah, no.
No. So very quickly, even 1930s, 1940s, they realized you need memory.
Or it ends up consuming a lot of space with vacuum tubes.
Roomfuls of space and generating so much heat.
Is that what happened? Is that why computers were the size of huge industrial complexes?
Yeah, because vacuum tubes.
I never understood why the computers were that big. I just knew they were, and that's what they said. And then people would move on like, yeah, you put in these punch cards. And I was like, but why is it that big?
No, we had to wait for the invention of the transistor and then the integrated chip, but that's later. right now, beginnings of even, I mean, breaking. Okay, you've seen the Enigma machine and the code breaking stuff in World War II in Bletchley Park. It's an amazing story. Several movies made of it. The Imitation Game is one, and it's a bunch of rotating dials. Well, it's really one of Babbage's. It's electrified Babbage machine, but at the same time they were using vacuum tube arrays computers to break Nazi codes. So it's a little competition between these two groups, and they're both working okay. But I mean, how many vacuum tubes can you have? And they're expensive, and they're hot, and they fail. I mean, light bulbs burn out, right? So do vacuum tubes. And if one burns out, I have 10,000 bulbs here. And it's not like, hey, that one's off. I'm going to go replace that bulb.
So much worse than Christmas tree lights.
Yes. It's like, it's not off. It's just not working. And they don't physically look any different.
Oh.
And it would take you a while to chase through your memory array, find the vacuum tube and replace it. And you'd expect 1 or 2 to fail per day.
Wow.
And take half an hour to find each one, probably.
Is that like the original glitch or the original bug?
Interesting.
Yeah.
Bug in the machine. I'm not sure. But it would have driven computer scientists to distraction because, back in Babbage's day, you couldn't trust the analytical tables. Well, now they couldn't necessarily trust the output of their machines because you don't know that every bit is working properly. Arg. So we need memory. How do we have memory? The earliest memory, I don't even understand how it works, but it was sound waves in mercury.
What?
And I think it was temporary memory because when the wave got to the other end, it would disappear. So you could store information in a mercury wave and then read it at the other end a second later, half a second later, something like that. But the memory was only sequential. You had to read every bit that came through. You couldn't do anything else. The first random access memory was a CRT. The old-fashioned fat computers.
Yeah.
TV screens.
Yeah.
Not even a television, not even a TV screen, but a television. They're like
tube TV.
Yeah, tube TV. They're like 2 foot thick, and the front is curved.
Totally bulbous. It kind of looks like a over supersized version of your outdoor house floodlights. On the edge of the house.
No, it looks like a TV, man.
Well,
that's what I grew up with. This is normal.
I'm saying this for the kids. I'm saying this for the millennials. Those big bulbs that you have on the corner of the housetop that shine down on your yard.
Yes,
that was tube TV.
Like the comment I made a couple of weeks ago about I watched one of the early Doctor Who's the reboot of Doctor Who on BBC. And they had flip phones and fat TVs. This is 2000 or something like that.
Yeah.
I was like, what? Things have changed fast. Anyway, so he took a TV-like thing and put a metal screen in front of it. And by going up and down and left and right on that metal screen, he could tell which pixels on the TV were on or off because the pixel at the front of the screen would make a charge. And so he could change whatever pixel on the TV he wanted. We didn't call them pixels then, but you put points anywhere on the TV you wanted. That was random access memory. You could store anything you wanted.
Oh, wow.
But the number of data points was restricted by how small a dot can you make and how small a dot can you detect on your metal screen in front of it. But boom, there you have a computer memory system, a very awkward one. At the same time, people were working on magnetic storage. Spinning disks and platters and all sorts of things like that. And it's, that's basically what we had up until SSDs came up. That right word, SSD? What does it stand for?
SSD does sound
solid
funny.
State device. Is that what
it's solid state drive?
Solid state drive. Okay. But even, a short time ago, my last computer had a solid state drive, and the one before that, had a platter, which was magnetic storage. Cassette tapes, 8-track tapes, reel-to-reels. It's all magnetic storage.
It's funny to think about now that my mind has gone there, how these things could have been called something different.
Yeah.
We called them hard drives. They could have been called spinning drives. It could have been called magnet drives. They could have been called metal records.
Yeah.
They could have been called different things.
Well, remember the laser disc?
Yeah. Laserdisc, or holographic disc was supposed to be a thing.
All right, so we needed memory, and we needed it quick, and we needed it early, because you can only store so many bits of information in your working memory. And we know that for computers too. Almost everything on my computer is stored in an inert state on the hard drive, which is an SSD. Almost none of that is loaded into active memory. And I can store a whole lot more stuff on my drive than I can work in my computer. And so early computers, you run a calculation. Well, you have to save that and then run another calculation. Maybe save that, or take the first number and compare it to the second number, and then you can do another calculation. Everybody knows that. I mean, when we do math, we have to do something, then do something else, and then do something else, and do something else. It's a stepwise process, especially when you're dealing with nothing but ones and zeros. Because if you want to multiply 52,000 by 7, that's an awful lot of ones and zeros. And so you got to break it down into pieces and do something and then save that in memory, do something else, save that in memory, and then maybe add it all up at the end, something like that.
And you don't need a lot of memory for a handful of ones and zeros, but yeah, with that collection of calculations, I can see why it starts to add up. Like nowadays, what does the most common computer have? Maybe the smartphones, if we say that those are the most common computers, they have 4 to 6 gigabytes of RAM.
Crazy.
Yeah.
Crazy.
But they're making insane numbers of...
That's 6 billion vacuum tubes.
Right.
What?
Them's a lot of data.
Yeah. Hey, you remember a long time ago when we talked about, it might have been even episode 1, greatest theory ever. We talked about the discovery of, I will have to do this. My very educated mother just served us. In order to discover Uranus, they had to do a lot of calculations by hand on the places where the planets were, Jupiter and Saturn, versus where they're supposed to be. These two guys, maniacally over months, months and months and months, at least 6 months, ran 5,000 hand calculations or something like to that order.
Wow.
In order to say, oh, there's another planet.
Wow.
And that's incredible.
Yeah.
That is so trivial today.
Oh.
You put that into Excel or into Starry Night on your cell phone or whatever, and it just calculates it for you. But it's actually doing a lot more work than those guys did. Those guys were in a base 10 system. Computer's binary. There's a lot more a lot more analytical steps in calculating the position of a planet on a computer than a human can do on a piece of paper. So why do we use computers? Because they're so blindingly fast.
Yeah.
And because the calculations are so easy, it just does an awful lot of calculations really quickly, and it very quickly eclipses the fastest human being.
Wow.
And that's the secret of computer. That right there, that is, we could stop right with that point. That is the secret of the computer.
Dang. That is so cool. It's like a superhero movie's origin story about the superhero, but this was the computer's origin story.
Yeah, I like that.
In the Carter cinematic universe.
So guess what the first real use of a computer was? Earlier than the ones we've been talking about, 1800s computer. Guess what the first use was?
Well, they originally started with textiles.
Yes.
And then nautical navigation.
Sure. But the first real world application where the world said, oh, thank you, we've needed this.
Calculating weather patterns?
Oh, no, we're even close to that. It was tabulating census data.
Oh.
It would take the census department 8 years to tabulate a census that had to happen every 10 years.
Wow.
And the population was only growing. And they wanted to collect more information. And so they made a system of punch cards and they ran it through and very quickly got all the data they wanted out of the census.
That is awesome.
So yeah, navigating ships, punch cards, looms. So all sorts of really cool applications for early computers. And today we look at cats on the internet.
Oh no. Well, like you started with, they are really dumb boxes.
They are totally dumb boxes. But you asked the question, what's a pixel?
Yes.
What is a pixel?
Well, I'd say it's a point of light,
It's
or
a point of light on a
or
screen.
the lack
Okay.
thereof.
Okay. But what does a computer think that pixel is?
Oh, well, the number one, or no. Man, I can't wrap my mind around it.
Well, in an old style monocolor display, the old green and white displays or something like that, that was ones and zeros. Is a memory array, and the memory said, light the spot up or don't light the spot up, a 1 or a 0. And so if you had, I don't know, let's say a 16 by 16 character display, and each character was an 8 by 8 array of ones and zeros, you would need that much memory to store what's on your screen. And so you would have one place on your computer that was writing things to the screen memory, and another place that was reading that as your cathode ray was scanning left and right and up and down across your screen. And it was reading the memory quick enough so that when it got to that point, 1 beep, 0001 beep, 01 beep, and it was happening so fast that your eye did not even see it blinking. So it has to happen more than 30 times per second. But there's two systems, one that would write stuff to the screen memory and one that would read the screen memory really fast. And they didn't talk to each other. But that's the essence of what a pixel is. A dot, a point, a thing in memory. The problem is our pixels today can have millions of colors.
Yeah.
And brightnesses.
So that's a lot of code.
A lot of code. And so your computer is writing to the screen memory area a lot of information. And it's not, back in the day, it was a single byte would control a pixel, and that byte would encode brightness maybe and color. And so I don't even remember what the numbers are anymore. I should, but like red
255 or something
like that. So today we have, so the first color computers, they had 8 colors or 16 colors or something like that. And that was in 3 bits, you could encode 8 colors. In 4 bits, you could encode 16 colors. In 1 byte, you can encode 256 colors. And so the system would say, okay, here's a byte. I'm going to read the next 8 bits. Oh, it's that. And it goes to a map and says, oh, it's that color. And then it would say, okay, I have my red, green, and blue pixels. I'm going to adjust the brightness of each of them according to this map that are already the color map saved in the computer somewhere. And we do that now with millions of colors. I don't know how many bits we use. Is it 32 or 64 bits per pixel? Something like that. And it just allows us to have all these colors. And that's what a pixel is, a memory location with a lot of bytes. Multiple bytes, tons of bits. And it just holds the information for what we want to see. The computer doesn't know what it's doing. We tell a machine, when this number comes, pull that information from this other spot there, and then light up, we don't have a cathode ray anymore, but light up this little spot on this flat thing in this brightness with this colors of these 3 things that the human eye can see. That's a pixel.
Wow.
Before we go, though, I want to talk about my favorite computer that I just learned about ever.
I was going to ask you, what in the Ask Dr. C a question section.
Okay.
What is your favorite computer ever?
Okay. Well, that might be the Commodore 64, my first ever computer, which I think is still the best computer ever built. Might be the K-Pro 4, the world's first portable computer with maybe a 5x5 inch monocolor screen that my mom got. And she had a professional typing service back in the 80s with her own computer. Ooh-wee. But actually, it's going to be U.S. patent number 2667304, awarded to Robert S. Wallach and Torkel E. Torkelson, my grandfather, January 26, 1954. I'm not exactly certain what they did, but they patented, and this is in the Smithsonian.
Wow.
It's an adding machine. Now, the old school adding machines, you click, 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 and you pull the handle. Ka-chunk.
Yes.
This one is electric. It has a plug.
Huh.
So it looks like a modern calculator.
Wow.
Except it has the numbers.
I'm looking at a picture on Rob's computer. It looks like it's going to print the receipt too.
Yep, it has a receipt printer. It
And
has
the
the
space
numbers
bar
0
is-
through 9,
And the space bar is turned vertical, but that's just the equals button, maybe?
probably.
The enter button?
The
so
enter
to speak?
button. Notice the red button is a negative.
I love it.
I
It's a
think-
beautiful piece of design work.
I think they may have invented the adding machine that has a subtract function.
That is so cool.
Maybe not. I'm not sure, but it was important enough.
Mm-hmm.
So this is a couple of years my grandfather worked at IBM in upstate New York, which I knew nothing about because my mom was a younger child. The family wasn't living in upstate New York when my mom was growing up. She has no memory of this. So I didn't hear anything of this. My cousin from one of my mom's older siblings has been talking to me lately. I'm like, what? Smithsonian? And so I had to look this up. I must find one of these.
It is a very cool looking old fashioned hunk of metal. They're well designed. I understand why this would be in the Smithsonian.
Yeah.
And what does that brand logo say across the pink labeled surface? It kind of looks like a G, but it's in cursive. It kind of reminds me of Coca-Cola's lettering.
General.
But then are
I
those
think it was
just dots underneath General?
I think it was the General
Electric? GE?
No, the General Adding Machine Company or something like that.
Wow.
Now, did he get any money for this? No. They assigned the patent over to the corporation that was paying them to build it. This is back before people would get royalties and things like that. He was just a worker. He's a real smart guy doing analytical ideas and idea development for other corporations. And he actually his name's on a number of different patents.
Incredible. Wow. Guys, this is going to be in the show notes. I'll probably put the picture up on my Instagram if you don't put it up on your Instagram so that we can make sure it's shareable. So neat. I often geek out about the design of technological things, and
It's just pretty.
This is for a 50s era design. It looks like something quintessential, even down to how they colorized the photo of this device.
You know what? I know what that thing smells like.
Really? How would you describe it?
Ozone. Because it plugged in, it would have gotten warm. It would have been producing ozone. It's made of plastic. I can identify that smell.
Wow. We got more than we bargained for. When I was going to ask you the question, what's your favorite computer? I did not expect such a good story. That is awesome. Wow. Man, so cool. Do you think that there's more we can say about computers in a future episode?
We didn't even talk about Alan Turing.
Please. Yeah. But we're going to have to make that a part 2.
Yeah.
So good.
We didn't even talk about the integrated circuit. We didn't even get to the invention of the transistor.
Yeah.
I mean, we've gotten nowhere. But the goal here was understand what a computer is.
Yeah.
And when you get to the ones and zeros things in Charles Babbage stuff,
right.
Without that, you don't have computers. One
of the most fascinating things about computers today to me is that underneath all these layers of the modern components of technology, it at a very rudimentary level still functions the same ways in the at the bottommost level.
At the bottommost level, it's a bunch of chicken scratches.
Yeah, it's incredible.
It's you 1, 2, 3, 4, make a cross for 5. I mean, that no joke.
Yes.
That's what this is. We're counting by ones.
And I'm holding my iPhone 12 Pro that I'm using for my notes. And I'm thinking about how high tech this thing is. It's better than anything that Captain Kirk on the Federation had from his tricorder.
Mm-hmm. And it can only count to 1.
So cool. So thank you everybody for joining us on this quest. It would be awesome if you would share Equinox with someone that you know that would enjoy it too. We write links and show notes for each episode, so if you want to refer to something that Rob has already mentioned in today's episode, there's a good chance that you'll find a link to it in the show notes along with episode 69. And you can get more of our content if you have joined Equinox Plus membership through Patreon. A link to the membership page is available in the show notes. And do check out Biblical Genetics, Rob's other project, on YouTube for his latest videos, and join the discussions in the comments because it's a pretty cool way to access Rob's computer memory. Yeah. Can I say that?
I guess so.
Okay. And if you want to find me, I'm at JCS Darnell on Twitter. Until next time, goodbye, Rob.
Goodbye, Joe.
You've been listening to Equinox.